you're all set to go.
Thank you. And again, thank you all for organizing this. Paris would have been nice, but I must say this 8-bit world is growing on me. So I'm hoping even after the pandemic, hoping to visit again, maybe with my family, stay a bit longer. But for now, I'm at Chicago in the physics department. And I'm going to talk to you about, this talk is essentially a relationship between two things that are quite different on the face of it. On the one hand, we'll have the physical dynamics of a given protein, meaning what happens to that protein or how it behaves when you poke at it or pull on it in physical space. And in particular, how it relaxes back to its stable state. And on the other hand, we'll have something more evolutionary in nature, namely how the function of a protein changes when you modify the protein through mutations, 1 at a time, 2 at a time, and so on. And so the talk is essentially about a relationship between these two that is a mechanistic basis for epistasis. And the main message is going to be that when on the left-hand side, if the physical dynamics conspire to have a mode gap in its physical dynamics, then that tends to constrain the sequence to function map, the ruggedness of the sequence to function map, and this concept of epistasis that Farouk just gave a very nice talk on. So this is a theoretical proposal that just appeared a couple of months ago in this publication. And I'm going to give you the theoretical proposal along with some supporting evidence in the literature already. But the basic underlying mathematical idea also generalizes to epistasis in a cluster of interacting genes and not just in a single protein. Right? So the idea is very simple. The idea of epistasis has already been introduced, but let me just mention it. So it's essentially the non-additive effect of mutations, right? So you take, let's say, one protein, you make a mutation here, a mutation there, then you make both mutations. How does it affect some function you care about, right? Is the total just the sum of the two effects? If it's not, the difference you call the epistatic coefficient for that particular pair. But maybe instead you could choose 10 different sites along the protein, make all pairwise mutations, and you could end up filling out a matrix of this sort. Now, people care about this for a host of reasons, like we just heard. Some people care about it because it might offer mechanistic insight into how a specific protein works, or it might help you engineer a particular protein. On the other end, it might help you understand how proteins evolve to pick up a new function. But in all these cases, the general sort of the naive expectation is if you go ahead and measure epistasis, say for 10 sites or 15 sites, and you find a bunch of numbers, strong numbers, some positive, some negative, the generic expectation is, oh, maybe the sequence to function map is highly rugged. Right? It's essentially a spin glass-based expectation. You plug it into some expression like this. And that has consequences. It makes things seem complex. And for example, if it tells you that you're going to have to do many experiments to understand or predict properties of this protein, just doing single point mutations maybe doesn't tell you anything about what will happen if you make a pair of mutations. Maybe you need to also do all triples and so on. On the evolutionary scale, it might mean that the evolution of this protein is pretty constrained and contingent, right? It's a pretty rugged landscape. What mutation you get first might decide which fitness peak you climb and things like that. Now, that's a naive expectation, but it turns out, mathematically speaking, that's not necessarily the case. If you have a bunch of strong values like this, it could be that you're getting all that epistasis simply because, or rather you can summarize that epistatic matrix as one global nonlinearity, let's say like a threshold function, applied to a linear underlying trait. That is, maybe the sequence is really contributing additively to some trait, which is this summation. Can you see my pointer? Oh, let me laser.
Yes,
pointer.
yes, we can.
Okay. So maybe the sequence is contributing additively to something, and then you just happen to measure a nonlinear function of that. And then you're essentially Taylor expanding it and thinking you're seeing epistasis, but actually there isn't very much. I'm just realizing I have a funny background, which I didn't mean to. If you don't mind, I do care about these things. There we go. I'm proud of my office. I've got nothing to hide. Oops, sorry, that was, all right. So some data sets can be summarized as a nonlinear function applied to a linear underlying trait. One simple example of this is if this matrix turned out to be rank 1, for example, you could just complete the squares and just get a square of a linear trait, right? And those fitness landscapes of sequence to function maps can be much smoother and simpler. Right? And in fact, for many real data sets, people have shown, for example, this paper of Arvind can indeed be summarized like this as a global nonlinearity, right? In fact, even Anne Flo, this paper of Anne Flo's is related to, and Ned Wingreen's is related to a similar idea. The question for today, though, is what is the mechanistic origin of the left and the right-hand side? When should you expect complex sequence to function maps and when simpler ones? The naive guess is that if you have strongly interacting residues, if different sites of your protein are strongly interacting with each other in complex ways, you should expect the left. They're essentially not interacting, but then you just happen to measure some nonlinear function of some underlying property like protein stability, you should expect the right-hand side. And the only point I want to get across today is that, in fact, if you have very strongly interacting residues, that's a generic way in which they'll give rise to global epistasis. That is, if those strongly interacting residues conspire to create a collective mode, like a collective mode that's much slower than all the other relaxation modes in the system, you should expect the simple kind of epistasis. Right, so that's the only point I want to make. And I'm going to just give you some rough intuition. You can look at the paper for the details. So imagine you have a protein with a, when you have a protein, people have, for a while now, have been computing its normal mode viewed as a mechanical object, essentially. There are many ways to do it. You could do MD simulations. Some people do mechanical models, but it doesn't matter. At the end of the day, you can get a spectrum of relaxation modes of this protein if you perturb it. If there's a mode gap, what it means is some motions of this protein are way easier, mechanically speaking, than others, right? Are way softer than others. Now, consider a theoretical, two theoretical elastic objects. The one on the left has no mode gap. This energy spectrum has no particular large gap. The one on the right has a gap. The one on the left, if you poke it in 3 different places, it's a disordered material, you poke it in 3 different places, it'll deform in 3 idiosyncratic ways. But the one on the right will deform mostly in the same way, because no matter where you poke, if the mode gap is particularly large and you have some coupling to that soft mode, will mostly deform in the same way. That is, deformations will be stereotyped. Right? Hopefully this is intuitive to you, even if you haven't thought about mode gaps or elastic materials. Right? Now, that's for forces, but mutations are effectively complex but local forces, right? You replace one amino acid by another. So what's true for forces, you could expect might also be true for mutations. That is, you replace one amino acid with another. On the left-hand side, you'll get 3 distinct or idiosyncratic deformations. On the right-hand side, it'll be pretty stereotyped. Now, what's the consequence of that? This is all just structural, but let me actually, going down the road of structure a little more, let's visualize it in this way. These axes are meant to represent the high dimensional space of protein structures. The wild type is some point here. And now just consider 2 epistatic cycles, meaning you make a pair of mutations A, B, A plus B, and measure the epistasis. You also make C, D, C plus D mutations. On the left-hand side, A, B, and C, D have no relationship to each other. That is, in this high-dimensional space, these mutations will take you to completely distinct parts of structure space, right? The deformations due to A and B will be in some 2-dimensional space. C and D will be elsewhere. There's nothing holding them together. But on the right-hand side, I'm claiming because of a mode gap, you'd expect them to mostly lie in some low-dimensional manifold, maybe even one-dimensional if there is just one soft mode, right? All of this is structure, but now finally let's add function to it. Right? And function, just imagine any function at all, some function that depends on structure. I'm really not going to specify what it is, but just pick your favorite function and plot its contours in the space, right? And make it a complex function, a nonlinear function. When you draw these contours, you immediately see that the mutation A, B, and A plus B have epistasis. In fact, both left and right pictures, you'll have strong epistasis. But the difference is on the left-hand side, the reason A, B, and A plus B are epistatic, and C, D, and C plus D are epistatic have nothing to do with each other. They are because of nonlinear aspects of F in completely different parts of structure space. Right? So those two coefficients are just independent coefficients. But on the right-hand side, at least if you think about it for a bit, what you can convince yourself is that there is really one nonlinear function that explains all epistasis, not just for this pair, but even if you added another pair, EF and E plus F. And that nonlinearity is simply how this fitness function F changes along that soft mode. Right? Now, for this, the fitness function itself doesn't need to rely on the soft mode. I'll get to this point again, but just the way the fitness function varies along that soft mode, let's say it's nonlinear, that's the origin of all epistasis. And if you think through that, you'll see why this is just global epistasis. So in the paper, we go through sort of a perturbative argument as well for this. The details are not insightful, but one aspect is maybe somewhat helpful. If you take a generic expansion like this, and then plug in this elastic Jacobian with some spectrum of modes, what you can show is there's exactly one soft mode with an infinite mode gap. So this epistatic matrix will end up being rank 1. And the higher order ones will again be rank 1 tensors. If there are two mode gaps, if there are two soft modes, you'll get a rank 2 matrix, and so on, which are known to have sort of smooth sequence to function maps in spin glass theory. Right? So that's the theory. Is there any evidence that, and then the main idea behind the theory, you remember, was that mutations, the effect of mutations gets stereotyped because of the physics of the underlying protein. And it turns out many people have been looking for relations like this for other reasons. One comprehensive analysis is this old paper. What they did was took 35 different protein families. In each protein family, they took crystal structures of proteins taken from different species, right? These are in sequence, they've diverged quite a bit. There are many mutations between them. And do structural PCA. And you find, let's say, only 4 principal components, right? So structure has changed only in a 4-dimensional submanifold in structure space. Then, right, that's the effect of mutations. But then they take one of those proteins and do a physics analysis on it, compute normal modes or something. And what they find is that the directions in structure explored by evolution through mutations is mostly contained within the softest normal modes that you obtain from a physics analysis, an elastic analysis of any one protein in this family. Right? And they show that for many families. There are many other papers which do something similar, but for like one particular protein or a few mutations in one protein or something like that. The main weakness in all of that kind of analysis is that the way people compute normal modes, you may not want to trust because it's based on some MD simulation or an elastic network model. A more stringent test that we hope will come online soon enough are based on experiments that can directly look at soft modes, like this one from Rama Ranganathan's lab here at Chicago. So these are pump probe experiments where you take a protein, poke it with an electric field, and take a series of X-ray snapshots, right? Like just 100 nanoseconds apart. So you can actually watch the protein relax back. You can actually see the mechanics of the protein, the transient mechanics of the protein. And then the hope is to compare that to mutagenesis for a more stringent test. So I've pretty much told you the main idea I wanted to tell you. I just have 2 more slides in which I want to sort of generalize this. Because so far I presented it all in a very mechanical context. But really the general relationship is slow, like a mode gap in physical dynamics constrains epistasis. So some people think of proteins in this way as a molecular ensemble, not really a mechanical view. Let's say a protein has 3 states, and really a wild type sequence defines an ensemble on it, meaning a set of occupancies for those 3 states. And then you mutate the protein, maybe it changes the energies of those states, and as a result, it changes how much you occupy those states, right? But even this picture, our results hold, because if you think about it, the steady state, the ensemble people talk about, is really the solution to a master equation. It's the steady state solution to a master equation. The master equation describes how the protein hops around between these states. But if you don't just look at the steady state, you look at the full master equation, you also have details of how you relax to that steady state, right? That is, you have a whole tower of modes that describe how you get to that steady state. And it turns out, if those relaxation dynamics have a mode gap, that is, there is one stereotyped way in which you come back to that wild type ensemble. So if you take this protein and perturb it physically by changing temperature or something else, the way it comes back to the wild type ensemble, if that's stereotyped, it turns out, again, epistasis will be global. And here now the function can depend on the occupancy of these different states. Right? So it's a physically a different picture of sorts, but mathematically a similar argument. And going to another scale, you can apply this logic to multiple interacting genes. So for example, in this paper, they took, and many people have done this kind of thing. You take bacteria, grow them in, say, 17 different conditions. And then you do mass spec, look at protein expression levels. And what you find is, despite having tried 17 different conditions, you need only 2 or 3 principal components to explain what's happening, right? Inspired by that, here is a piece of math. So when you have a gene regulatory network, imagine that each time you perturb it in these 17 different ways, maybe the initial perturbation to expression levels is highly idiosyncratic. Maybe it lives in 17-dimensional space. You put it in acetate versus galactose. Maybe the initial perturbation to the physiology is high dimensional. But you could imagine there are some regulatory networks where the initial perturbation quickly decays down to one slow manifold, and then slowly comes back to the wild type, to the homeostatic point through that slow manifold. That is, there's an initial transient that's idiosyncratic, depends on the details of the condition, but then the longer time scale relaxation is always along, some a particular low dimensional manifold. And the mathematical logic that I've been laying out essentially shows, if you apply it to this context, it says, for this kind of system, if you now make a mutation, that fixed point will again tend to move only along this one-dimensional manifold, at least for small perturbations. And as a result, epistasis should again be global. Right. So with that, I think I just want to summarize. So the statement is just a simple logical structure, right? If you have slow modes in dynamics, then mutations will explore a low-dimensional subspace, and as a result, epistasis is constrained in a specific way. Right? And the one aspect of this that I particularly like is that in this framework, we're not appealing to direct function of these soft modes or slow modes. These slow modes or soft modes need not have any function. For example, in the protein context, usually when you think of allostery, you often think of it as having a direct function, say regulation. Here, even if that mode did not have such a function, a direct function, we're arguing that it has this other function, sort of indirect function of reducing the ruggedness of the sequence to function map. So the main weakness of this argument that I've been making is that I had to assume that the structural effect of mutations is small, right? which is not true for all mutations. There are mutations that will unfold a protein or make big perturbations, but there are many mutations that only make a small linearized perturbation to the structure. A key point I want to note is that we're not assuming the functional effect is small. The functional effect can be large. The structural effect needs to be small. On the other hand, the nice thing is, as I've shown you, it can apply to all kinds of slow modes. And also, the fitness function does not need to be related to the particular soft mode. So once you have a soft mode, any function of that protein that just depends on structure will satisfy these constraints. Oops, that was not meant to be animated. So I just want to thank the people who did the work. In this case, this work is by Kabir Hussain, a postdoc, my group. Here are the other people in my group working on related projects, and also my collaborators on related projects. With that, I'll stop. Take any questions.